So, in the first video, we talked about samples and different characteristics of those samples. Now we're going to talk about measurements and what we actually do or what we collect on those samples. So, a measurement is a process of comparing a value to a standard unit. That is the book definition that we have, but really a measurement is just some type of value that has a unit. So if you think time in seconds, or distance in inches or centimeters or whatever, okay? That's all a measurement is. And we can have two types of measurements. The first type being qualitative, which is more subjective in nature. It requires human judgment, so thus the subjectiveness, via observation or evaluation. So a qualitative measurement might be if we had a bunch of kids in a room with toys and obstacles or whatever, and we had like a motor development specialist go in and observe the kids and write down what types of movements they're doing. Okay, so that would be a qualitative type of measurement. Quantitative measurements are more objective in nature. They usually carry some type of numerical value, okay, and it requires the use of instruments to measure quantities. So think distance, force, time, frequency, occurrence. So if like the number of free throws somebody makes out of 10 shots possible, or something like that. Okay. A test is the way in which we collect the measurement. So it could be an instrument, a tool, or a protocol. And then the evaluation of that measurement is the process of determining the worth of the data you've collected. So if we're looking at an example of a vertical jump, the measurement of the jump would be height in inches. Let's say it's inches. The test would be the protocol or the task that the person's doing. So maybe we're having them do a counter movement jump with a vertec. Okay, so the actual task would be the counter movement jump. The tool that we would be using to collect the measurement would be the vertec, which is like the big long pole with all of the little like slits that you like try to slap. So if any of you have taken 301, which all of you have or should have, and you've done the vertical jump lab, if they still have it, you've seen a vertec before. Okay, but that would be the tool. And then the evaluation maybe is we want to compare jump scores of a volleyball team pre and post season. Okay, so that's how we evaluate the worth of the data. Did their jump height increase as a result of a certain type of training program or what have you? Okay. Data is the result of a measurement. So jump height in inches, that is a data point. Or oftentimes we'll also call this raw scores, which are kind of like the raw data that we have collected from the samples that we are measuring. Statistics related to samples are the mathematical technique used to organize, treat, and present data for further interpretation. So that's the point of this class, right? I will give you guys data sets every week. Sometimes how we treat and organize the data will be dependent on the type of test that we're doing or what analysis we're running. And then the results that we get is how we present to whoever our audience is, so that we can say, well, this is what these results mean. These are the interpretations that we're inferring onto a population from our sample. So characteristics of useful data should be these three things here. Now, there's a lot of crossover between these terms, and sometimes students get them a little bit mixed up. So I've kind of have like keywords that you can think about when you're trying to apply these terms to different situations. The first characteristic of useful data is reliability. So this is the consistency or the repeatability of measurements taken. I like to use a dartboard or dart throwing as a good example. So reliability of a measurement or consistency, right? You could throw a dart at a dartboard a bunch of times, and if you keep throwing that dart in the same location, that would be a consistent performance, right? If we were putting markers on people for some type of 3D motion capture, the consistency of the placement of those markers on each bony landmark or anatomical location on the body, that would be an example of reliability. Validity is more related to the accuracy or the appropriateness of the measurement. So does the instrument measure what it actually sets out to measure? Or is the measure that we are collecting actually representative of the outcome we're trying to get? Okay, so if you want to see how well someone will run a 10K, you wouldn't necessarily ask like, oh, what's your 1RM bench press? You would likely ask them to do some type of exercise stress test to get their VO2 max and then infer what their 10K time would be based on their VO2. So validity is related to accuracy, reliability is related to consistency of measurement, and then objectivity is related to the absence of bias. Okay? So typically students will look at this in terms of another form of reliability, which is more specifically directed to who is actually running the test, so the tester or rater. So oftentimes objectivity is also referred to as inter-rater reliability. But usually objectivity, we maximize this by using machines or softwares rather than people to collect measurements. So, if somebody's using a stopwatch as somebody's, running a 100-meter dash, that stopwatch or the person pressing it, it's more of a biased measure because they're going off of when they see the person pass the finish line, right? If they anticipate clicking the stopwatch before the person crosses, if they click it after, right? There's a little bit more variability in the type of measurement that you would get, which we call bias. So instead, we would use maybe a tool like a timing gate, which has more sensitive and calibrated sensors that will pick up when the person actually passes the timing gate. So objectivity, sometimes related to the testers or the raters or the investigators that are doing studies, but usually we maximize objectivity by using different tools or protocols so that we have a greater consistency of measurement with less bias introduced. Classification of data. We have two primary categories that we can classify data in. The first being non-parametric, the second being parametric. Non-parametric data does not meet the assumption of normality. Parametric data does. Okay? So I don't know if any of you guys remember parabolas in algebra, but it's basically like a U-shaped graph that's based off of like quadratic functions. So a parabola or this U-shape is where we end up getting normality. And really it's like an inverted U. So it's like McDonald's but with one arch. That is the concept of normality. And we'll touch on more specifically what normality is in a couple of weeks. But there's this idea, maybe some of you have heard of a bell curve, where if we collected a sample, we should have some people on the low end, some people on the high end, and most everybody in the center, where it's like that's where our average is. Okay, so that bell curve is the concept of normality. Non-parametric does not adhere to normality. Parametric data does. Within each of those categories, we also have two different types of data. So non-parametric data is typically more qualitative in nature. It's descriptive. right? And it's the two categories that we have under non-parametric data are nominal data and ordinal data. Nominal data will be primarily what we use in this class, and it's more often what you will see in the kinesiology field in terms of research. For parametric data, this is more quantitative in nature, so think numerical values that we measure on people, and it can be split into interval data and ratio or scale data. Okay, I say scale, and really scale represents both interval and ratio data in the SPSS world. But when I ask you guys more specific examples in class, like, oh, how would you classify this data? You would want to be more specific and say interval or ratio, because there are defining characteristics that differentiate the two from each other. Okay. Ratio data is primarily what we work with in the kin field. We do have several examples throughout the semester of interval data, so it's not out of the question, but nominal and ratio data are the most common ones used in this class. If we take a deeper look into each of these types of data, nominal data, again, a parametric qualitative type of data, it is often also referred to as categorical data, meaning that when you collect your sample, there are certain characteristics, although your entire sample may have at least one common characteristic, there are different characteristics that are going to end up separating your groups from each other. Okay, so meaning they are mutually exclusive so that one group does not share the same primary characteristic with another group, right? So if we're looking at like classes, or classes, that's the only thing I can think of, or like the year in college, right? Freshmen cannot be sophomores, sophomores cannot be juniors, juniors cannot be seniors, and then all of the other different types of combinations that we could get in there. Okay, so the type of class or the year you are in school would be considered a nominal type of data because it assigns a category to a subset of your sample, and then that's how you end up organizing people. Sometimes we will associate these categories with data labels. So in the case when you're using numerical values to kind of like be a placeholder for the descriptor of your category, those numerical values cannot be used in mathematical calculations. So 1 is not less than 2, 2 is not less than 3, 4 is not greater than 2. We can't make those translations because those quantitative values do not actually have any meaning to them. Okay. Some other examples of nominal data would be if we were looking at different sexes, right? So males versus females, those are mutually exclusive categories. We could also look at if we had like some type of treatment or intervention. The treatment or experimental group could be one category, the control group could be another category. And the way that we actually sample or conduct our measurements on those groups could be either within subject or between subjects. So we could have a group of people, we take a baseline measurement and then we do a post-test measurement. We could have a group of people that just are controls or they get a placebo, and then we have another group that is actually exposed to a different type of drug or experimental factor, whatever. Okay. So that's nominal data. Ordinal data is the other type of non-parametric data, and it's often also referred to as ranked data. So it is categorical in nature in the fact that we still have a labeled variable, but it is going to assume, or categories will assume, a specific order. The order does not indicate a quantitative difference between adjacent ranks. So similarly to nominal data where the numerical values don't really carry a lot of meaning, ordinal data is kind of similar in that respect. So different examples we might have are places that people get in a race. Okay, first, second, third, fourth, fifth, all the way through 10th. The actual ranking of that person doesn't necessarily tell us how fast they ran the race or if they ran the race faster than somebody else. So first place and second place, it does not distinguish how much first place ran faster than second place. Same thing if we lined up people from shortest to tallest, or if we took different pain scales. Okay. There is a logical order to each of those, but the actual quantitative difference between time points or between data points is not really emphasized within the rankings themselves. For our parametric types of data, interval data was our first type that we had listed on that slide. And this is a quantitative measure with a meaningful order. So if you think of a number line, right, there's 1 comes before 2, comes before 3, comes before 4, right? There's a meaningful order to the data, but there's no true zero starting point. So for interval data, you can have both negative and positive values within the same scale. Common examples of interval data are temperature, right? So if you think of 0 degrees, that is an actual degrees. It's not the starting point of our temperature scales because we can go both above 0 degrees as well as below 0 degrees. Joint range of motion is a good example for the kin field. So if any of you guys have done a Thomas test before, it's to look at hip flexor flexibility or mobility. And the person hangs their leg off of the table. So 0, or we kind of like are looking at the relationship of this thigh to the horizontal. If they're completely horizontal or if their leg was parallel with this reference point, then that would be a 0 degree measurement. They could also be below that horizontal, which would be a negative measure, and if they were above horizontal, that would be a positive measure. Okay, so 0 is not the starting point, rather it's an existing point within this fluctuating scale of negative to positive values. Ratio data is the last type of data that we have in our parametric category. It's also quantitative with a meaningful order, but how it differs from interval data is that it does have a true 0 starting point. So either you're going to start at 0 and have positive values, or you'll start at 0 and have negative values, but you won't have both positive and negative. So examples would be weight, height, and time. You can also think distance, force, EMG recordings, which actually, nope, that's not a good example because you can have both positive and negative. So EMG would actually be a good example of interval. Anyways, generally, this is the type of data you'll be working with, though. So oftentimes when I say, oh, what type of data would you classify your dependent variable as? Most of the time, it's ratio. Okay. I had a student actually share a table. I had to recreate it for accessibility reasons in the slides. But I think this is a really nice summary table to show you how each of the types of data are different from each other. We've got different descriptors labeled, meaning that there is some type of label that is assigned to the data, whether it be category, ranking, if it's just the variable names for both interval and ratio data. Does it have a meaningful order? Is there a measurable difference between quantities? And then is there a true 0 starting point? So nominal data, strictly categorical, strictly labeled. Ordinal data, strictly categorical, but it also has some type of logical order to it. Interval data, same thing, but it doesn't have a true 0 starting point. Ratio data checks all of those boxes. Okay, so when you're going through examples in class, you can use this table to kind of reference back to see or use like a process of elimination to figure out what type of data you're working with. This week, I've also included a data classification practice activity. It's a separate PowerPoint. When you actually do the presentation, so you start the presentation, it will act like an interactive game. So you'll get an example, you'll have nominal, ordinal, interval, ratio options. You click on a corner, or whichever corner you think matches the type of data you see as the example. And then if you hear a swoosh sound and it turns red, that means you have an incorrect answer. If you hear a chime with green, that means you have a correct answer. Okay, so go ahead and give this a practice if you feel like it, and then I will see you in the next part of the lecture.